So the main thing I want to get everybody to understand is just to get people thinking and excited and arguing and so forth. It's not like I'm giving you data that I want to stuff into your head and have you repeat it and believe everything. So anyway, a lot of what everybody knows about networks are actually false. And the way networking tends to be taught is as if TCP/IP arrived on tablets from the sky in its awesome perfection, and nothing else ever existed. And if in a book it talks about anything other than that, it's only to make sort of snide, non-technical comments about it. But this is not the way to teach. So my philosophy on teaching is to take a conceptual problem, like you plug into a network, how do you get an address? And I say, here's like 7 different ways I can imagine doing it. Here are the pros and cons, trading off latency against overhead, whatever. And then I'll say, and by the way, IPX did this, AppleTalk did this, IPv4 does this, IPv6 does this. And I've heard that some professors push back and say, why is there stuff in here that my students don't need to know? With this model of a student as having this tiny brain that you fill with facts, and if you tell them anything that is not on a recruiter checklist, if the recruiter is not going to say, do you know anything about AppleTalk, then having them hear about it wastes, precious brain cells. But that's, I believe, not the way to teach. I believe if all you care about is IPv4, you will have a much deeper understanding of it if you can see alternatives, and especially if you're ever going to want to design something new. It's so important to have seen other things. So people keep coming up with the same ideas with no notion that it existed before, often doing it less well than was done before, and this I just find annoying. That's the way my books are, and that's the way that I teach. So standards, they're so confusing. I always like to get to the heart of what's different about technology A versus technology B, if there's sort of 2 things that are kind of similar. And nobody does that. Nobody knows them both. So, okay, I go get the specs, and I get these 2 huge specs, badly written, all with their own jargon for no good reason. And so I'm trying to wade through them to get to the heart of what's really different about these. And so I might try to save myself some time. I'll ask an expert in A, how does it compare with B? And he says, A is awesome and B sucks. And then I ask a B person, get the opposite answer. But then if I have waded through it and I find out some cool things about B, I tell the A people, actually, B has these other features. It works better in this case because of the way they handled this. And no problem. The A people steal the ideas. And so both A and B are moving targets. Nobody actually cares what's actually in their spec. They just want their spec to win. So basically, it's natural to think of standards bodies as well-educated technologists that are carefully weighing engineering trade-offs. But a much more accurate way to think of them is as drunken sports fans. It's like, rah, rah, my team. So there's other things, like what if you do it scientifically? So I saw somebody trying to compare 2 technologies, A and B, and his was A, and it seemed to me inferior according to every criteria I could imagine. But he was trying to sell it to the executives. And so one of the things he was showing was throughput. So on technology A, he was getting 4 gig of throughput. Technology B got 1 gig of throughput. And he'd measured it, and it was on a PowerPoint slide in Excel. So it's now science and could be safely repeated and quoted and all that. But I was sitting there thinking, I can't imagine what would make technology A have more throughput. Every intuition, I says, would be the opposite. So I actually innocently said, were you by any chance using a 1 gig physical link when you were measuring B? And he said, yeah, that's all he could find in the lab. So he had measured technology A on a 10 gig link, got 4 gig, technology B on a 1 gig link got 1 gig, and now he's proven that technology A gets 4. So you have to really, don't believe things that you hear. They're not necessarily true. If you're actually measuring something, you're not really measuring technology A versus B. You're measuring one implementation of A against one implementation of B. Buzzwords. These drive me crazy. And yes, they're incredibly useful for impressing customers, but that is the only thing you should do with them. So when you use a buzzword, like SDN, let's say, it terrorizes 80% of the engineers. They're sitting there saying, oh my goodness, everyone else understands what it is, but I don't really understand it. But the remaining 20% of people are confident they know what it means. And if you say, well, what is SDN? They'll go, oh, it's sure, whatever. And then you ask somebody else, and they go, oh, it's sure, and where has nothing to do with And I've actually kind of separated SDN into like 7 orthogonal things, none of which are new. Some of which are fine things, but you didn't need to invent a word for it. And that's another whole talk I could give, but at any rate. So yeah, when you're talking to engineers, never use buzzwords. Don't say, well, in this project, should we use SDN technology? Don't do that, because the purpose of communication, especially with engineers, is the idea in my head is supposed to go into your head. And if we're using buzzwords in different ways, that's not going to happen, because he'll have a different image. But yeah, with customers, it's fine. If a buzzword comes along and everyone thinks it's cool and nobody knows what it means, by all means, tell the customers, oh yes, we're the foremost proponents of this thing, and whatever it is. You don't have to change what products you're doing. You just use the buzzword. So think critically. Don't believe everything you hear, even if it's in a textbook, even if your professor told you. Now, with some professors, if they tell you something, you better remember it so that you can parrot it back on the test. It doesn't mean that you have to believe it, but good professors will not be all pedantic about this is the truth. They'll actually really enjoy engaging in a debate. But yes, you have to be careful when you're taking a class that you know which kind of professor you have. And don't repeat things you don't understand, because if they're not true, the more widely heard, the more widely said something is, the more entrenched it gets, and the more people feel really stupid for saying, well, why is that really true? So yeah, the field is really confusing. So here's a bunch of examples of things that everybody knows. So one is, if you ask a networking expert, why do you need both IP and Ethernet? They will confidently tell you, because IP is layer 3 and Ethernet is layer 2. Well, I'm going to talk about that. I'll have a whole bunch of slides about it. But that's nonsense, as I'm going to, a foreshadowing of what's to come, is Ethernet is not a layer 2 protocol. It's a layer 3 protocol. It doesn't matter what you call it, but I'll show you, the definitions of things. And so the right question to ask is, why do we have 2 layer 3 protocols? And that's an extremely deep thing that you will not learn from any textbooks other than mine. And I wish more people would do that. Another one that's really cool is people say, security is built into IPv6 and it's just an add-on to IPv4. And it's like, what are you talking about? Well, the germ of truth in that is that there's one protocol called IPsec, and it can work equally well with IPv4 or IPv6 or AppleTalk. It doesn't really care what's underneath it. But the spec says it's mandatory to implement for IPv6, and it's optional for IPv4. Well, those are just words in a spec. It turns out there's more implementations of IPsec for IPv4 than for IPv6. And last I looked, which was a long time ago, admittedly, there were more implementations of IPv6 without IPsec than with IPsec. And furthermore, IPsec is not equivalent to security. Pretty much anything you could do with IPsec, you can do with SSL. So this is such a weird statement that I keep hearing people repeat. And then SDN is revolutionary stuff. You know, for a while, every conference I went to, there was a keynote talk by somebody saying, what a privilege it is to be born at this point in history when SDN is transforming the planet. And then they'd have panels where, you know, I would hope that in the panel they would be debating what it is and whatever, but the panel title would be something like SDN, Panacea or Miracle. And then, you know, people from various companies would all talk about how important SDN is to their company, and no one would actually say what it was. Which, as I said, is many different things. It's a moving target, you know, as they think of more things, and it's not a revolution in anything. So an example of something confusing. So now I'll talk about the whole Ethernet and IP layer 2, layer 3. So yeah, what is this about? One is a layer 2 solution, one's a layer 3 solution. What does that really mean? And so in order to do this, first I have to explain about layers. So maybe you've all heard of the ISO layers. It was, you know, it's sort of a way to think about networks. ISO was a different sports team, you know, rather than IETF. And so they defined 7 layers. And so I'm going to explain those layers, but I'm going to call it Perlman's layers, which will be obvious in a minute why I'm doing that rather than saying ISO, because I will modify it slightly. So layer 1 is the physical layer. How do you signal a bit to the other side? What is the cable? What are the pins on the cable and the shape of the connector? Layer 2 is how you get a packet of information to a neighbor. So layer 1 allows you to signal bits. Layer 2, you have to somehow be able to signal in the stream of bits. This is the beginning of the packet. This is the end of a packet. Here's a checksum. Layer 3 is the thing that actually forwards packets. So there are these sort of intelligent agents that receive a packet, make a decision, and forward it on the other side. Layer 4 is sort of end-to-end stuff, like, for instance, numbering the messages so you can put them back in order or retransmit things that got lost. And it's a protocol between the source and the destination, and that's like TCP. And layers 5 and above are boring. That's what So why are we forwarding Ethernet packets? Ethernet was intended to be layer 2 and not forwarded. But it is forwarded. So how did that happen? And there's no logic to it. You just have to understand the history. So what exactly is Ethernet? Well, you know, there's no way to understand it without understanding the history. So before Ethernet, I was the one designing layer 3 of DECnet. So what does a layer 3 person do? I, you know, defined the data packet format and the distributed algorithm by which, you know, this intelligent agent receives a packet, computes this forwarding table, which gives it enough information to decide how to forward the packet. So that was me. I was doing layer 3. And then along, ta-da, came Ethernet with great fanfare. So, and by the way, computing the forwarding table, what kind of distributed algorithm would you use for that? And maybe you all know this, but I won't take that long. You could do it with a central node. And this is not a new idea. That's one of the things SDN is saying, oh, why don't we do it with a central node? Well, you know, where everyone reports the topology to a central node, and it calculates everyone's forwarding tables and distributes it. Well, you could do that, and ATM did it that way. InfiniBand, which still exists, does it that way. It's not really a new idea. Or you could do it with a distributed algorithm. That's the kind of thing I was doing. I happen to prefer distributed algorithms because, I'll explain. Yeah, I mean, they react more quickly to a link going up or down. Because the algorithm that I'm about to explain, it's called the link state algorithm, you figure out who your neighbors are, and then you flood to everybody else. I am Radia. I have a neighbor George at a cost of 2, a neighbor Alice at a cost of 3, and so forth. And so everybody gets this information, and they can calculate their own forwarding tables. So if a link goes down, information about that propagates outward as quickly as physics can carry the information, and everyone updates their own table. Whereas if you had a central thing, you have to let the central guy know. You have to send a message to him that the topology has changed. He has to recalculate everybody's tables and then talk to everybody and distribute it. So I think either one works fine. I happen to prefer distributed. So in a distributed algorithm, you plug the thing together, preferably with no rules whatsoever, just like Tinker Toys, build your network however you want, and then the switches adapt. The switches are the green circles in there. And the kind of a distributed algorithm is where they glean whatever information they can and then calculate stuff. So, sorry. So in this slide, the top is a picture of a network. There's 7 nodes there. A and B are neighbors at a cost of 6. And so forth. So that top little picture should be clear. It's just a picture of a little network. And underneath it are the link state packets that each node has generated. So A has, the thing on the left says, I am A, I have a neighbor B at a cost of 6 and D at a cost of 2. And everyone sort of sends everybody else their link state packets, so everybody has this identical database, which tells you all you need to know about the network so you can calculate paths. So that's what I did. What I'm actually far more proud of than the spanning tree algorithm, which was this hack that I thought was a bad idea. But anyway, we'll get to that. So, so I was doing layer 3, and then along came Ethernet. And so I said, whoops, here's a new kind of link which has different properties. So I have to do little diddling with my routing protocol to handle this new kind of link. So the original Ethernet was this protocol called CSMA-CD. It was a way of having a bunch of nodes on a single wire sharing the bandwidth. So think of it as, like a bunch of people in a conference room, and there's no person standing in front calling on, who should speak next. So CS is don't be rude and interrupt. Carry your sense. Listen before you talk and don't talk if someone else is talking. MA is multiple access. Be aware that you're not the only one in the room, so don't hog the bandwidth. CD is collision detect, so that because you can't listen to multiple people at the same time, if you're talking and somebody else interrupts, then both of you should stop. And it's amusing to me. I seem to have been born with CSMA-CD ingrained in my brain, but I go to meetings and there's other people that don't. So when they feel like talking, they just do. And they don't do CD either, so you can have like 3 of these guys talking at the same time, and it gives me a headache. But at any rate, the property of this protocol was it only scaled to a certain physical size, like within a building maybe, and only to a few hundred nodes or so. And if you tried to load it too much, if too many people were talking, you'd have collisions like all the time, and the useful amount of bandwidth would go way down. But I saw Ethernet as a new type of link, and so I had to do little modifications to the routing protocol in order to handle it. So an example of something I did was if you naively said this link with 500 nodes should be reported in the routing protocol as 500 nodes, each of which have 500 neighbors, the link state database would get really big because the size of the link state database is sort of the size of the number of links. And so what I did was I said, okay, I will pretend instead, I will invent an extra node I call a pseudonode, which is the Ethernet itself. And instead of the picture on the left where everyone reports connectivity to everybody else, I invent a new node called the pseudonode, and everybody just says they're they're attached to that. So you have n+1 nodes and n links instead of n squared links. So, little things. But it was a link in a network. It was not a network. They should have called it Etherlink and not Ethernet. Now, if you look at the Ethernet packet, you put a destination and source on your data. And then if you look at a layer 3 packet, it looks kind of the same. There's this extra mysterious field called a hop count. The reason for that is in a distributed algorithm, if the topology changes, you can't snap your fingers and everybody simultaneously reacts to the new topology. For a little while, the forwarding tables will be inconsistent, and packets will kind of wander around. And you have the hop count so that you will put them out of their misery, and they won't be using up this bandwidth by going around in circles. But the Ethernet people did not put a hop count in, and it wasn't because they didn't know about hop counts. It was because it never occurred to them that anyone would be forwarding this packet format. It wasn't intended for that. It was intended to be layer 2. So it's easy to confuse Ethernet with layer 3. Now, way back when we were saying that we needed a bigger address size than IP, IPv4 has 4 bytes, Ethernet has 6 bytes. Why couldn't Ethernet have replaced IP? It has a bigger address space. Well, Ethernet is not appropriate for for the internet, even though it has a bigger address space. First of all, it's missing the hop count field. But also, one of the geniuses of Ethernet is the flat address space, that when you buy something that plugs into an Ethernet, it comes born with a unique 6-byte ID, so you don't have to think about addresses. You just plug them in, and everyone has a unique address. Well, that's very nice for sort of auto-configuration of fairly small nets. But in something like the internet, you like to be able to draw a circle around a portion of it and summarize it with one block of addresses, which you can't do with flat addresses. So why are we forwarding these Ethernet packets? So back to I was doing layer 3, along came the Ethernet, and people got all confused, and they were building applications that went directly on Ethernet. So in their network stack, they had Ethernet, and then they built their application on it. And so I was running around telling people, no, you still need layer 3. And they said, oh, go away, Radia, you're just upset because no one needs your layer anymore. And I said, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that. So they built their stuff. It was great stuff. It would have been just as good had they done it correctly, which was on top of layer 3. But they made lots of money for the company, so they were all like heroes. And it was kind of annoying to me because I knew they had done the wrong thing. But at any rate, so I was in kind of a bad mood about this whole thing when along came my manager one day, and he said, Radia, we need to design a magic box that will sit between 2 Ethernets and let someone over here talk to somebody over there, which is what my layer was doing. But it only works if the end nodes cooperate and implement the same packet format and behaviors or whatever that layer 3 expects. But so the constraint was that we wanted to, after the fact, invent this magic box that would work even though the end nodes didn't have layer 3. They just thought they were speaking on a single CSMACD link. And there was not a single spare bit in the Ethernet packet. We couldn't modify it in any way. And there was a hard size limit to the Ethernet packet. So given those constraints, I think the solution is sort of as good as one could do. So the basic concept was that this magic box listens promiscuously to every single packet on every port, stores it up, and then when the ether is free, if it's an Ethernet, or it gets the token if it's a token ring, then it forwards it onto the other ports. And then sort of another cool idea is that rather than having to forward every packet everywhere, if you look at the source address of a packet you've seen on this port and learned and notice which port it came from, then you know you don't have to forward something onto other ports if the destination is there. So in this case, this box has learned that A is on that port and X and C are on that port. So if A transmits a packet with destination C, it only has to forward it on that port. If A transmits a packet with destination J, the box doesn't know where J is, so it has to forward it on both other ports. So the problem is this doesn't work if there's multiple ways of hearing from the source. Also, if there's any loops, the packets are just going to go round and round and round. So what could we do about that? Well, one thing is we could say to the customers, don't do that. It has to be in a tree. But then what if they make a mistake and miscable it? Or wouldn't it be nice to have backup paths where you allow multiple ways, but only use one at a time as a hot standby? So the solution was to do this spanning tree algorithm, which was kind of the bridges. The magic box is called a bridge, talk amongst themselves, figure out a loop-free subset of the topology, and only forward data packets on those paths. But the other paths are available in case the spanning tree decides that they're actually needed. So you have a physical topology, which is anything you want. The green things are Ethernets, the round things are bridges, the lines to the green things are ports on a bridge. And So the bridges, after they run the spanning tree algorithm, will have turned off some of the ports and turned them into dotted lines. So that means the path, if A transmits a packet and the destination is X, it will go from A to bridge 11, 7, 6, 2, 14, 4, and 3 in order to get to X. And you might think, well, that's silly. If the spanning tree algorithm were a little more clever, you could have gotten better paths. But no, if you want one shared loop-free subset, you're not going to get optimal paths. Think of it as, imagine if the topology were one big circle. You'd have to chop it someplace. And then people on either side of the chop have to go around the long way. So the story of this is just so cool. My manager asked me, he said, oh, you do distributed algorithms, come up with this thing that breaks all the symmetries, no configuration. And furthermore, he thought he was being witty. He thought it was going to be like really hard. He said, and furthermore, make it scale as a constant. So no matter how many bridges and links there are in the world, the memory necessary to run this should be a constant, which is a ridiculous thing. Nothing scales as a constant. It might scale linearly if you're lucky. It's more likely n squared. So he was going to be on vacation the next week, and he told me this on a Friday. And this was before cell phones or people reading email or electricity or, whatever. It was a long time ago. And so that night, I was thinking about it, and I realized, oh my goodness, it's trivial, and furthermore, it scales as a constant. And the reason for that is that to run the spanning tree algorithm, you have to remember the best spanning tree message you've heard on each port. So when you receive, on this port I've stored the best spanning tree message I've heard recently. When another spanning tree message comes in, I have to compare the two, and there's a trivial little check to see which one is better, and whichever one is better, I store that and throw the other one away. A spanning tree message is about 50 bytes, and so if you have 5 ports, it takes 250 bytes to run the algorithm. So I was really excited. I could prove that it worked. I knew just how to make it work and so forth. Monday and Tuesday of the next week, I wrote the spec in enough detail that the implementers got it working in just a couple months without asking me a single question. But this is like Tuesday, and I couldn't concentrate on anything else because I had to show off to my manager. So the remainder of the week, I worked on the poem that goes along with the algorithm. And when he came in on Monday, I presented him with the spec and the poem. So the poem is called Algorhyme, because every algorithm should have an algorhyme. And so the poem is, I think that I shall never see a graph more lovely than a tree. a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the route must be selected. By ID, it is elected. Least cost paths from route are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So then there was a really cool story that I only found out about after the fact. So the sales guy was selling the very first bridge. And this was to the world's most sophisticated network customer at that point. And so the sales guy went, and the people were saying, oh, but, we're doing all this fancy stuff with all these layers of networks, and this is talking to that and whatever. And the sales guy was saying, yeah, it really doesn't matter. It's just going to work. And they were saying, no, we have to talk to the engineers. We're doing, look at all this stuff. And then he said, it doesn't matter. It's just going to work. So they had they bought it, and it didn't work, and they were really angry. So when field service went to and this was the world's simplest topology. It was two Ethernets in one bridge. So when field service went to find out what the world's most sophisticated customer had done with the world's simplest topology, they discovered this. Which is, orange cable in the ceiling looks like orange cable. And indeed, everything was working perfectly. I'm glad I actually thought of that case, by the way, where the bridge said, I don't need to forward packets, so I won't. But if I ever do, I will. And the only thing that wasn't happening was that packets were not using the ESP protocol or whatever to leap from one to the other. So anyway, CSMA-CD died out long ago. As a matter of fact, within a year or two after the spanning tree bridges came out. A variant of it works on wireless links, but on wired Ethernet, there's no CSMA-CD there anymore. It's all point-to-point links and bridges. Which brings me to a chance to rant about something else. Inventing new words for no good reason. I can't cope with words. I was a math major, so you say, for the purpose of this conversation, we're going to say that yellow means the things you wear on your feet or whatever. And it's like, sure, I can cope with that. But so one day I showed up at work, and people said, Radia, nobody cares about bridges anymore. They only care about switches. I said, okay. What's a switch? And they explain it to me. And I go, that's a bridge. And they go, no. I say, oh, sorry, okay, can you explain it to me again? And they do. And it's like, that's a bridge. And so then I finally said, okay, what's the difference between a bridge and a switch? And I've had various answers of people who are absolutely sure this is a brand new revolutionary thing. No one cares about bridges anymore. They say, well, it has more ports. A bridge only has 2 ports. And it's like, yeah, so digital happened to only sell ports with 2 bridges, bridges with 2 ports, but that doesn't mean that it was intrinsic to the thing. It's like having a car that comes out in orange, and nobody thought about having an orange car before. So do you invent a whole new word for this thing? Right. Or that it's faster. Or that it's done in hardware rather than software. But anyhow, a bridge and a switch is exactly the same thing. So why not get rid of... So that was back then. That was why we had to invent the bridge/switch thing, whatever, and forward Ethernet packets. But these days, everyone has agreed on a single layer 3 protocol, which is IPv4. And everyone has it in the network stacks. So why don't we get rid of all of this spanning tree Ethernet and just hook everything together with IP routers? All the excuses for it way back then don't exist anymore, so why are we still using it? So the reason is there's an annoying property of IP. And if it were a different protocol, indeed, we could do that. So let me explain the annoying property. IP requires every link to have its own unique block of IP addresses. So if you have a block of IP addresses and you want to number your corporate network, you have to carve up the address space to have a unique block on each link. You have to configure the routers to know which blocks are on which ports, and you better get it right. And if a node moves from one side of a router to another, it has to change its IP address. Now, that's kind of annoying. And networks could be designed so that you could change your layer 3 address and no one would mind, but they're not. But just because IP works that way doesn't mean that layer 3 has to work that way. So this is actually a very deep thing that most networking experts don't know. And I would love people to really assimilate it. So there was a layer 3 protocol done by another sports team, which was ISO, and it was called CLNP, which stands for Connectionless Network Layer Protocol, I think. And it had 20-byte addresses. So IPv4 has 4-byte addresses, IPv6 has 16-byte addresses, CLNP in the late 1980s existed and had a 20-byte address. But not only was the address bigger, but it had this really cool property, and this is slightly deep. In IP, everybody on the same link must share the same block of addresses, and nobody must have an address in that block anywhere else. Here, the top 14 bytes is a prefix shared by everybody in a cloud, in a quite large cloud. So within the cloud, it's a flat address space. You can move around in the cloud and keep your layer 3 address. And your address inside the cloud is the bottom 6 bytes of the address there. The top 14 bytes specifies which cloud you're in. So if you kind of compare this with the way IP plus Ethernet works, in IP gets you to what IP perceives as a single link. But we don't want a single link. We want to have some cloud with a flat address space you can move around in. So IP depends on Ethernet to create the what looks like a single link to IP, but yet gives you a flat address. And inside, it does whatever Ethernet does, which is, spanning tree, which doesn't give you optimal paths, or trill, which I've actually talked about at a previous USENIX, and there's only so much time. So if you and furthermore, once you get to the Ethernet link, you have to do some sort of awkward, expensive thing like ARP in order to get your address there. If you compare that with CLNP, the top 14 bytes, you can have as many levels of hierarchy as you want, just like with IP, gets you to the cloud. But then you don't have to do ARP. You're routing based on the bottom 6 bytes. It's right there. It's like gluing Ethernet and IP together. But also, furthermore, layer 3 knows about how to route within the cloud as well. So inside the cloud, it keeps track of where all of the end nodes are. So with CLNP, the end nodes actually advertised, I'm here, and the routers kept track of you. You could even have multiple ports, and it would route to you the best way. So anyway, and in terms of hierarchy, if you have one prefix per link, you have to carve up the address space and do a lot of configuration. If you have one prefix per cloud, like CLNP did, inside the cloud, no configuration of the routers. You just plug them together, you just plug the end nodes together, and as long as you stay within that cloud, you don't have to change your address. Somebody has to sort of let the cloud know what the 14-byte prefix is, but other than that, no configuration. So the single worst decision in the history of mankind was that in 1992, people said, IP addresses are too small. Why don't we replace it with CLNP? At that point in history, all the vendors had it implemented. And because I was doing DECnet, I also thought we should have bigger addresses, way before that. And instead of saying, wow, I want the glory of inventing a new packet format, and everyone will know me as the inventor of this new packet format, I saw CLNP and I said, I don't think we need 20 byte addresses, but sure, why not? It seems fine. So, so DECnet was, phase 5 was also CLNP, the same data packet format. So it was widely deployed and working just fine. People built quite large networks out of it. So imagine, so that was suggested by a lot of, people, but just a few people in, the other sports team went berserk. And they were saying, you can't rip the heart out of the internet and put in a foreign substance. And they'd complain about all sorts of bizarre things, like they didn't like the session layer in ISO. And it's like, this has nothing to do with the session layer. It has to do with replacing layer 3 with a different packet format, which happens to have been invented by another sports team, but other than that. And people showed how it took them only a couple of months to have TCP running on top of CLNP, and automatically all of the internet applications worked. So imagine if it weren't for these, just people due to not invented here, and I don't want to give the other sports team the satisfaction of saying anything they ever did was worthwhile. Because of that, we did not, they did not say, okay, let's use CLNP. But had they done that in 1992, instantly, the internet would have had 20 byte addresses. So, but they were thinking, well, whatever this is, I'm sure, we could invent something like so much infinitely better. How about IPv6? Will that save us? They've had, 20 extra years to invent it, so it must be awesomely better than CLNP would have been. But it's not. It works just like IP in that every link has its own block. It's just bigger blocks. And, so not only did we miss the market window when it would have been trivial to switch, the internet was just this little researchy thing back then. And IP had not, out of necessity, invented all these kludges like DHCP and NAT. CLNP gave instant advantages like auto configuration, and furthermore, IPv6, if we ever get there, it's so much harder to change the internet now, is not as good as it could have been. So I want people to understand that. So now I'm going to talk about some somewhat neglected areas for research. Because there's students here. So one is resilience despite malicious participants. I'll talk about that a little bit. And the other is usability. So I don't have either one of these could, again, be an entire talk, but I just sort of want to introduce the topic. So malicious participants, this is also known as Byzantine failure, which is as opposed to a fail-stop failure. A fail-stop failure is where everything's working perfectly and then suddenly it halts. And that would be like really nice of it, but things don't necessarily do that. So you can have a node that's misfunctioning either because it actually has malware in it and it's being malicious, or there's bugs or misconfiguration or hardware errors or whatever. And there's all sorts of things that we do in networks that can be subverted with a very small number of malicious participants. So one of the most delightful papers I've read recently, and there's I assume these slides will be posted so you can follow this link, was how there was this crowdsourcing puzzle-solving thing where they had tens of thousands of participants, and it turned out one guy managed to just make the whole thing not work, and it's just amazing. And then there's things that can't possibly work, according to all of my intuition, but they do somehow. So Wikipedia, by all my logic, all my intuition, it should just be, given that anybody can edit it, it should just be filled with rants about Obamacare or something, I don't know. But it is the most, fantastic source of concise, well-written, accurate articles. How can this possibly be the case? I actually know of a mistake on Wikipedia, which I will not give you enough information to fix. But I know someone whose girlfriend was from some obscure country, let's say Albania or something. And it's not that country. It's some other even more obscure country. So in the Wikipedia article about, this country, it says, their main export is potatoes or whatever. And, it's this size and whatever. And then it says, and famous people from there consist of blah, blah, and blah, blah, and blah, blah. And he added his girlfriend's name to the list, which I think is really charming, and nobody's ever noticed that. But Wikipedia, how can that possibly work? And eBay, how can that possibly work? You decide you want to buy shoes, and so you go searching on it, you find the kind you like, and there's this merchant from a country that you never heard of, and a merchant you certainly never heard of. You send them money, and shoes appear. This is, quite a miracle. But now I'll talk about, things that will fail with malicious participants, but how to design it so that it is resilient. So, there's 3 things that I have personally been involved in, and I'll talk about 2 of them for lack of time, rather than all 3. So I'll talk about the first and the third. And the second one is what my thesis was about. It was about how to design a network that guarantees that A and B can talk to each other as long as there's at least one honest path that connects them. And what is a dishonest path? Well, a malicious switch is one that can lie in the distributed algorithm, give false information, or flood the network with garbage, or forward packets in random directions and reset the hop count so it looks new, or do everything perfectly, but because it doesn't like you, it throws away all of your packets. And yet, that was my thesis, which turned out to be very simple, by the way. I proposed it, and everyone said, ooh, all the committee, that's an important, difficult problem. And I've never done anything difficult. I kind of look at it from all angles, and then I said, oh my goodness, I know how to do this, and it's straightforward, and whatever. So then I kind of shyly went up to a professor, and I said, is there any minimum length restriction on a thesis? And he said, well, it either has to be long or good. But at any rate, so that was my thesis. Let's see. I'll just tell, all right. So with limited time, I can only talk about 1 or 2 things. And by the way, when we get to the Q&A thing, I will answer questions about anything. It doesn't have to be stuff from the talk or whatever. And I'll be around in the next couple of days if you want me to go into more detail about any of these things. So the first thing is a PKI model that is resilient to having malicious CAs. So what's a PKI? What's a CA? A PKI is a public key infrastructure. It's a way for me to reliably know what your public key is. And if Alice knows Bob's public key, then he can authenticate, he can prove to her that he knows the corresponding private key. So Alice has to reliably know it, and it involves having a trusted third party known as a CA, or a certificate authority, or certification authority, that signs a document saying, I vouch that this number is Bob's public key. So Bob might send his certificate to Alice, or Alice might look it up in some kind of directory. So let's look at various models for how to build this PKI. So the first model I call a monopoly model. You find one organization that's universally trusted by all countries, all companies, whatever, which alone is getting pretty absurd. But you embed their public key in absolutely everything. Everyone has to get certificates from them. This is nice to understand and to implement. But what's wrong with it? Well, monopoly pricing. If you give one organization the more widely deployed it is, the harder it is to ever switch out that organization to a different organization. But also that one organization can impersonate anybody. So if you can find somebody in that organization to trick or bribe or threaten, you can impersonate anybody. The next model I call an oligarchy, where you come configured with 100 or so things. This is what's in your browser. And it does eliminate the monopoly pricing problem, but it's less secure because now any of those organizations can impersonate anybody. So now I'm going to sort of get to what I think will work. So chains of certificates. So instead of requiring Bob to present a certificate from one of the CAs Alice is configured to trust, he can have a chain of certificates. So Alice might be configured to trust X1, and Bob can give several certificates. X1 says this is X2's key, X2 says this is X3's key, and X3 says this is Bob's key. Now, every time you have, the anarchy model is like, also known as the web of trust. Every time there's a gathering of nerds, like an IETF meeting, I don't know whether you do that here, there's a PGP key signing party where, with some sort of ritual where you say who you are and what your key is, and people can sign certificates, and they can also donate them to these public repositories. And the idea is, if I want to get your public key, I look to see if it's configured in my machine, and if not, I try to piece together a chain from one of the things I've configured by looking through the certificates in these public repositories and trying to get to your name. So this, the problem with this, it's not going to scale from sheer size, with no rules and having to explore everything. But also, more or less, anyone can impersonate anybody. Once you poison this database with false identities and bad certificates and whatever. So now I'm going to get to the model that I recommend. So the first concept is, instead of thinking that a CA is trusted or not trusted, it's not a binary thing. Instead, say a CA is only trusted for a portion of the namespace. So a CA is kind of owned by an organization and controlled by that organization, and it's in their interest to make sure their CA is behaving properly in order to do certificates for their one organization. So the name by which you know me implies who you trust to certify my key. If you know me as Radia, Perlman, EMC.com, you would trust EMC to certify my key. If you know me as roadrunner279.socialnetworksite.com, you would trust them to certify the key for that name, or credit card, .bigbank.com. So whether these different identities are the same carbon-based life form is irrelevant. So you need to have a hierarchical namespace in order to make this work, and ta-da, we have it. It's called DNS. So each node in the namespace represents a CA. So if you look at, it's natural to kind of think of what I call a top-down model where everybody knows the root, and this is kind of the way DNS works. And the root certifies the key of the children, and that allows you to know exactly how to reach a name, but you still have a problem with a monopoly at the root and the fact that the root can impersonate anybody. So now I'm going to change the model into what I call bottom-up, where not only does the parent node in the namespace certify the key of the child, but vice versa. And so you can get from any place to any other place. You don't have to start at the root. You can even start with your own key. Now we're going to need another concept, which I call a cross certificate, where any node in the namespace can certify the key of any other node in the namespace. And you need that for two reasons. One is you don't have to wait for the entire PKI for the world to get connected before you can find keys. And the other is so you can bypass CAs that you don't trust. So if you have PKIs in two little organizations, you don't have to wait for there to be a root or anything. You could cross-certify, and guys in one namespace can reach the key of the other. And if you don't trust the root, for instance, you can bypass it by creating a cross-link, so that when you're in the namespace below the cross-link, You go up until you see the cross-link that gets you to the target name, and you go down. And note that, note this does not create the anarchy model, because you don't explore a crosslink to see where it might go. You only follow a crosslink if it looks like it will get you, if it will get you to an ancestor of the target name. So the advantages of this model is that the trust chains within your own organization do not leave your own organization. It doesn't matter if all the CAs in the rest of the world are compromised. It won't affect the trust that you presumably care most about, which is between entities in your own namespace, because the chains of trust will not leave there. And malicious CAs can be bypassed and damage contained. So so I'm somewhat running out of time, so I won't discuss the second thing. Another neglected topic is usability. And engineers should actually meet some humans, and then they would stop asking questions like, do you want to display both the secure and the insecure items? Or I was installing an email client and it said, do you want POP or IMAP? And it's like, I happen to know those are two email standards, but why would I care? And how am I supposed to choose? I mean, it's really absurd. So, so it's common to have to trade off usability versus security. So the more usable it is, the less secure it'll be. But the industry has managed to find that spot. So every site has different rules for usernames and passwords. It has to be at least N characters or no more than X characters. It must contain at least one of these, or it must not contain, whatever. So there was this great quote I saw on the internet. I wish I could attribute it properly. Sorry, but your password must contain an uppercase letter, a number, a haiku, a gang sign, a hieroglyph, and the blood of a virgin. So, and can we do worse? Yes. I had to set a password once at some site, and it said, your password does not meet our length, complexity, or history rules, without telling me what the rules are. So anyway, so I'm going to skip now to this quote. I do not want to hear we need better user training. I hate that. And there's something that I wrote in my book that I want people to really assimilate. So it's a quote, but I wrote it. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It's astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our protocols around their limitations. So, so yes, make your stuff compatible with people and don't expect the installed base to modify themselves to work with your thing. So I'm almost done. Protocols in life. Being a protocol person for the last 82 years, I can't help but just sort of notice protocols everywhere. So there are protocols that don't work. People do this all the time. We'll call you if there's a problem. It's like, no, call me in either case, because if you don't call me, what if you mistyped my number, or my phone isn't working, or whatever, or we'll call you if we want to hire you. Same problem, call in either case. Or one time I was in a hotel and they slipped this thing under the door. And it said, tomorrow at 2 p.m. there will be a fire drill. Ignore all sounds and behavior of the staff at that time. That seemed like a really bad idea. So, parting thoughts, what wins out in the marketplace isn't necessarily the best thing. So, for instance, English is a lousy language, but it works, and you can come up with something better, and as long as it kind of does what you need to do or can be modified, there's sort of no real incentive to change it. But you can't go around and say, oh, I know why English worked. Dutch clearly could not have worked because it has too many consonants, or whatever. And don't believe or repeat things you can't understand. They're often false. And also, this, in my book, I have these little boxes I call real-world examples to illustrate points I'm trying to make. So, for instance, I talk about, like with scalability, the wine glass clicking protocol, where you have to click with everybody. Doesn't scale really beyond like 6 people. So the one example that's everybody's favorite is to illustrate that you should know what problem you're solving before you try to solve it. And this anecdote is 100% true, and it will forever cement in your mind why this is important. And it's such a problem in this industry. People kind of hear about a couple special cases, they get all excited, start writing code. It doesn't work for these cases. They add warts to it and whatever. And you shouldn't do that. Think about what you're doing before you solve it. And so the example that will forever make you understand that is when my son was 3, he ran up to me crying, holding up his hand, saying, "My hand, my hand." So I took it and I kissed it a few times. "What's the matter, honey? Did you hurt it?" And he said, "No, I got pee on it." So thank you. That's it.
We've got time to take a few questions if someone wants to come up or shout out loud. So then you designed a protocol for the next time your son came with a complaint.
Right. My poor son. I mean, he's really good-natured. He's like a grown-up now. When he went to MIT, people were familiar with the book. When they found out he was my son, they'd go, "Oh, so it was you?" And he'd go, "I was 3." So, yeah, question?
So, given the background that you've had in networking and security for a long time, if you were to pick one problem that we should focus on today in this space, what would you put at the top of your list?
I think usability, maybe. As well as the malicious participants. So a lot of times people have, with the malicious participants, let me give you an example. You say, well, okay, I'm going to have 5 active things. So I'm going to have 5 active copies, let's say, of my data. And if I can modify it in any place, and any of them can tell the others to, change things. And I don't see super resilience because you have 5 copies on different continents. I see 5 single points of failure, because any one of them can go berserk and tell everybody else to compromise the data. So it's just sort of a way of thinking about things that you should be more aware of. So like with a cloud, you can store your data in 97 different places. Boy, it's really, really resilient. But can the cloud administrator who's feeling annoyed that day delete all of your data? So, and then just usability is such an unbelievable mess. I hate computers. Some people were talking about, I always loved them, and no, I don't. I sort of barely tolerate using them. I just, for the first time, I got a smartphone at EMC, and I don't know how to do most things. It sort of sits on my desk and makes little funny buzzing noises. I have no idea why. And I actually figured out how to read a text. I'm not, sure I can send one. But, it's good. We need more people in this industry that hate computers so that they design stuff for actual people. Things should be self-configuring, they should be resilient, and they should be stuff that you don't need to know. Right.
We just finished the first 2 days of this week on conference on storage and cloud. And one of the things that seems to be an emerging technology is putting storage devices directly on networks, such as Seagate Kinetic. What do you think of the issues of taking a spindle and sticking it on a network, and how do you secure it?
Well, yeah, security is kind of a weird word because it means so many different things. So you can't say, okay, here's this thing, make it secure. It sort of depends on what you mean by secure. So I can speak, just, on a network, and as long as there's kind of end-to-end security, I don't have to worry about intermediate devices modifying what I'm saying or whatever. But are you worried about DDoS attacks? Or, so I would hope that the end nodes can do isolation properly so that it's safe to mix and match these things. DDoS is another whole thing. How do you guarantee resources for each thing in a network? I am a firm believer in virtualization and cloud, and when I complain about buzzwords, when I say SDN, and at EMC, everything is software defined. I have no idea what it means, but it's just, hi, have a nice software-defined day, is kind of the greeting everybody gives. But then people say, oh yeah, just like cloud. And cloud, I actually think, is meaningful. It's sort of this place with virtualization, and you can have, instead of your own physical machines, you have, virtual machines that get carved out of there and look to you like physical machines. I mean, I think that's great. And network function virtualization is another thing that people say that I think is well defined. It's instead of having a separate box that's a load splitter, you implement it in in a VM, and if you need more capacity, you spin up more instances of it and so forth. But yeah, so anyway, so that's kind of an answer to your question is, how do you make it secure is first, like, which aspects of security are you talking about, and you would attack them different ways. DDoS defense is something else that I was thinking about for a long time and could be another entire talk, but yeah. Any other questions? Okay.
Thanks.
Yeah.
Thanks again.